information about the essay, partly because people were writing questions to the tutors individually and also to the discussion forum that suggested to us that some of you had not grasped the point of it, that we really did want you to focus on the discovery, how it changed conceptions, why you were interested in this and why it was important. And some people were not really reading the directions we sent out right at the beginning, and that's why we issued a more explicit, if you like, marking grid about the essay. It should not be difficult to make your essay and your lab report conform, if you like, to the new guidelines. If you've got any kind of sensible introduction to your report, if you have some data and if you have some results, there shouldn't be a great deal of difference between a report you have written and the report we'd like you to write. And similarly with the essay, if you had paid attention both to the original instructions and the clarification we put on Blackboard, it shouldn't be very difficult to put your essay into the format that we'd like to see.
Indeed, the marking grid is effectively a distillation of what we've already told you.
Yes, there shouldn't be any surprises on the marking grid. One difficulty is that as soon as we issue what we think is a clarification, it seems to create more problems for some of you. Some of those are understandable, like I have been asked, what does it mean to write scientific English?
A good answer to this is that we've been telling you to look at scientific papers. That is what you should be copying. So, for example, someone sent an inquiry saying, do we write our methods in numbers? No, you don't. We write out your schedules like that because we write them out as recipes. Look at how it is done in real scientific papers.
And understandably, that's something you haven't had a lot of experience of yet. But you should get into the habit of writing continuous prose. And bear in mind what we've been saying in the lectures about clarity and precision. It's something that I hope to come on later to, because I want to show you an example of some scientific prose that isn't completely clear. A good method is to read it out loud and see if it makes sense to you. If it doesn't make sense either grammatically or logically, don't write it down. Because if you don't understand it, no one else is going to understand it. Reading work out loud, and I do it myself with my own work, is a very good guide to the quality of your own English. Some of the questions we're getting are a bit perplexing, to be honest. We wrote that the report should be 3 pages and should have, I can't remember exactly the format, but there should be a design, some data, and some results. Someone asked me, does that mean the report should be 3 pages with design, data, and results? I'm sorry if that person's in the audience and if I've misunderstood their question, but that's the only sense I can make of it. We've also said the design should be a single page, and someone's asked me, does that mean 1 side or does it mean 2 sides? Okay, that's slightly more understandable, but no, it means 1 side. Critical thinking begins at home. You know, you are expected to be able to kind of interpret simple instructions, and we both of us try to write actually quite clear scientific English ourselves, and you ought to use some initiative to try and interpret our work. One reason for that is there are 400 students on the course, and if we had to reply to every one of these little queries, we would have literally no time to do anything else. So please try and use your judgment on this kind of thing.
Right, we're going to start by giving you some advanced feedback on some of the things that were happening in practice last week. And truth be told, I think we were both fascinated to see some of the things that people were doing. And I think it's been a learning experience for us as well, because one of the things it clearly illustrates is that how counterintuitive scientific thinking often is, and how hard it is to learn it. And so, what we're going to, what I'm going to briefly go through first, are some of the things we saw people do, and certainly if you fell into these traps, then I hope that this will be useful in patching things up for your writer. So this is advanced formative feedback for helping you report. Now, the first thing that did kind of surprise us is that many of you have picked up on the design thing, but one of the key threads to this module is experimental design, and the main place we are assessing how well you've learned it is in your practical and your practical data. So, I mean, good idea to have carried this into the practical, and also to bear this in mind, bring the elements we've been talking about out as you go through your writing. So, hypothesis, sample, so on and so forth.
Can I jump in there? I know that in biochemistry and molecular biology, you're doing a practical this week that involves writing a protocol and carrying it out. It seems that people are not transferring notions they've learned in this module into that other one. What we tell you isn't just something you're only allowed to do in critical thinking. You are permitted, and in fact you are obliged, to think about these things in other modules as well.
We will be displeased if come through next year and claim to have never heard of any of this stuff. Some of the interesting things we saw are students coming in with a really nice plan and then ripping it up as soon as they got into the lab. So with some of those we were able to get back on track. But let's see, this is not responding. So maybe is this the USB in, or is it getting it's low on views?
I put batteries in, it should be fine.
Okay. Maybe I think we need to manually switch over. So we go on to the next slide. Right. I've plagiarised a couple of slides from other people. So, this is one of Jeffrey's from earlier in the morning. And so, talking initially about simplest title for an experiment. And he was talking about his sleep drug. How might this be carried over into our practical? What in most cases we do. Thinking just about the title first. It's the variable most of you used. So the effect of ascorbic acid on because some of you done it in different ways, time of a start writing copy.
Remember, your X is your independent variables, the thing you manipulate. Now, what did you manipulate in the experiment?
Concentration of
ascorbic acid. Yes.
And your dependent variable is the thing you're going to measure, it's your outcome. So that's where your X and Y come from, and that's the whole secret of experimental design. You really must fix that into your mind.
Okay, and what did we say was the first thing you needed before you started out on any set of experiments? A hypothesis. So what's our... And in this case, you're going to kind of have two hypotheses. You're going to start with a weak one. What might be an obvious weak hypothesis here be? Okay, that's right. I've got a slightly weaker one still than that, but as you increase the amount of ascorbic acid, then the time increases. So that's nice. So I think come on to my suggested one next. Explain this. So what was our initial hypothesis? And Jeffrey's something along the lines of ascorbic acid delays appearance of colour in the start of reaction. So this is a very easy one to test. So we do it without the ascorbic acid, we get the colour straight away, we put ascorbic acid in, and we have a delay. Simple enough. And then we're going to go from, again, the effect of X on Y, and we've already touched on what we're going to do with that. So how are we going to move towards a stronger hypothesis where we are describing the relationship between the ascorbic acid and the time?
What evidence are we going to have for a stronger hypothesis? How can we make this hypothesis stronger?
That's right. So we're going to collect data and move towards a standard curve. So if we move to the next slide. Now along the way, there's an element of design here. One of the things we did see is people trying to change lots of things at once. And this was a bad idea. And the obvious thing is, if you're trying to change two things, for example, ascorbic acid and potassium iodide concentrations at the same time, then to do 5 data points for each, if you're going to completely characterize the system, you're going to need to do 5 times 5 measurements, 25 measurements, as opposed to 5, and that's even before we get into replicates. We'll come back later. So, not necessarily a bad idea to think about looking at more than one thing, so indeed we kind of encourage you to do so, but the best plan would have been to have done one thing first, and once you've got that system under control, by changing other things in one dimension, perhaps choosing one set of reaction conditions. Certainly, while we might be interested in a much bigger thing, the interaction of ascorbic acid and potassium iodide, that's a much bigger experiment. What would have been a wise one to embark upon in the time available?
And the whole point of science is to simplify what seems to be a complex situation. You can't control everything that's going on in your solution. You can't do multifactorial experiments. You can do a matrix design, but the simplest design for an experiment, the only one we asked you to do was if X, then Y. So it's not like cooking, where you think, okay, to make my cake rise a bit more, I'll put 2 extra eggs and more salt and more sugar and more vanilla, and I might add some baking powder and turn the oven down. You know, science is about simplicity, and it's not common sense. Most people think the natural world being complicated, then methods to try and understand it must be complicated. In fact, the opposite is true. You want to find simplifying conditions as far as possible. If your experiment only relates X and Y, then you've got a good chance of getting data.
We come to the next slide. Okay, so here is our set of data, a very idealized set of data. We'll come to that in a moment. And what follows from this, let me go through these quite quickly. Yes, so the thing that was missing so far, so remember to ask you, so what we didn't have in there is a control. Without ascorbic acid is our control, so this is another one as well. So we put everything in except the ascorbic acid, and the colour appears straight away. That's a 0 time control. So that gives us our next point, and then we come to this. And so what we have now is a stronger hypothesis. It's not just that as we increase the ascorbic acid, the time will increase. That line is a mathematical relationship describing that relationship. And if we ask Excel to put the equation on, that is the description of that relationship. Now, I've drawn these for straight line for simplicity, but certainly some of you were seeing a slight upward curve. Don't worry if you did, that's fine. It's clearly one of the ways that systems sometimes work. I'll be really interested to see the write-ups, to see what makes the difference between the straight lines and the curves, because presumably it's some slight adjustment to the results you saw. And then in practice, although we kind of turned this into the parlour game, pick the time, what you were actually doing when you were checking your time is this. You were testing this hypothesis by seeing if you could put in these conditions and hit that time. That is a very powerful test of your hypothesized relationship between ascorbic acid and time, and your delay, or disappearance. Okay, any comments or questions? And of course, this is one of the reasons why we were encouraging you to do your standard curve as we went along. Because this was your tool for doing it. We weren't asking you to do the standard curve or pointing you in the direction of the standard curve just as a task to be completed, as a sort of hurdle to be got through the practice. This was a working tool for visualizing your data and making use of it. So we had some people say, okay, I've done the time, do I have to draw the curve before I go? Well, by then it was rather too late.
What was interesting for me is that people who I know were in one of my tutorial sessions, where in all 3 of them we did get to the point of talking about standard curves. Some of those people abandoned the idea as soon as they got into the lab. They didn't draw one or see the point of it.
We will come to some of the reasons for that in a bit, and it does come into some quite interesting ways that people deviate from scientific thinking. Okay. However, we come on to the next slide. And this one's come from Andy Dalby. So where it all went wrong. And I think we'll be seeing examples in all of these. Getting your data. Well, we've already seen the advantage of displaying the data. We'll come to averages and the like in a bit. We aren't going to touch on correlations and causality, the probability will have a silence like that, and fiddling after the fact a bit as well. So did your data actually look like this? No. Well, some of you did some really nice pipetting. I mean,
I saw one, I was very impressed by one group. I'll spare their blushes by not naming them, but one group demonstrated to me, on the basis of a line like this, that they could hit their time exactly twice while I watched them. There's no doubt that they'd done the right thing, and in a sense they had tested their hypothesis.
So if we come to the next slide. So here we've got something maybe a bit more likely, where our data points are falling a bit to either side of the line of best fit. Okay? So this is maybe a more likely set of data. This is going to lead us into some of the important elements that you should also be thinking about. Can we come to the next slide? Okay. Our line of best fit is a mathematical relationship. So we never, almost never, want to see what I colloquially refer to as join the dots. So drawing a line from one dot to the next. And some people kind of do a sort of wavy curve in order to make it look like a line of best fit or a polynomial. That's not, this is not a proper mathematical relationship. So what we need is our line of best fit. I think that can sometimes be a curve, but a plausible real relationship. The only occasions when you maybe would do this type of thing is where you're looking at a series of measurements at different times of a series of events where those are not properly connected. So I suppose you might look at numbers of geese appearing in the sky in any particular month or some such. Any comments on that, Jeffrey?
No, I agree with that, but you're not in that situation here. You have a proposed relationship between your x and y, and so a line of best fit would be the thing to do. But if you were looking at a series of essentially unpredictable events, like how many cars pass in a certain time, then you might then join the dots.
And a couple of other things that might have gone wrong, though I have to say we didn't see many of these. If we come to the next slide, is this a reasonable thing to do? Why not? Because we're trying to make a prediction way beyond the data that we actually have. So
it's very important to bracket the time that you're trying to find. So if you're trying to find a time up in the 50s, you cannot do that on the basis of data points that don't reach that time.
Though I'll say in passing, we do tell you this, to do this elsewhere. The line we've observed effectively extrapolates to infinite substrate concentration, which is not actually an experiment we can do. Because, of course, we don't know whether the line is going to do either of these things. Truth be told, the bottom one is the one you more usually would see, but certainly we've seen upward curves in some of the data we saw. So you don't know whether this is going to happen, so our prediction, based upon extrapolating beyond our data, is not sound. So this is, again, something to be aware of in future. As I say, we didn't see many of you do it, more sensible than that. So, coming back to next slide, please. Okay, so this is not a bad set of data. We've got some noise in there, but it's still giving us a reasonably plausible line of best fit, which is actually still the line of best fit we've been working through along. But what if instead we get something like this? Any of you get data that look like this? Okay, so how do we then deal with this? What is our solution? Something more in terms of the experimental design. Why are the points falling all over the place? They haven't done the duplicates. That's right. So, so what is our answer here? How do we get around? This is because of variability. Betting isn't perfect. Maybe temperature is slightly variable. You have to hold in the cheap water. This is natural variability. Is throwing noise into the data. The solution to this is replicates. So increasing our sample size. So instead, we want to do something like this. So I would say for this, probably triplicates will be good. Okay? So we use replicates to try and reduce the noise. And another thing, of course, is that you could have, not strictly speaking, done replicates. You could have done lots and lots of different individual times. And that would also have filled in and tidied up your data a bit. But it makes something rather important we'll come to in a little bit less clear cut than it is from this.
Can I just say, with a lab experiment, a biochemical experiment like this, we of course can do independent replicates. We can take 3 data points at each concentration. We can't do that, for example, if we were testing a drug on a person. What we then have to do is just take lots of people and, in a sense, fill in the points, fill in the line with 1 data point for each person. So there are circumstances where you can't conveniently do replicates. In most lab situations you can.
But sample size is always going to be an issue. It's larger as you can. So, imagine that we are, instead of plotting all of our data, rather, we just plotted the means. What information have we lost from doing that? Who thinks we should have just plotted it? I've kind of given away what the answer is by the way I've asked the question.
I actually heard the right answer from over there somewhere when you said what we lost.
Sorry, can they please repeat it?
Yes. Yeah. I mean, you've lost any sense of the dispersion of the data. So.
That's right. So this is actually useful information, and also, of course, it means that if you plot the mean in, the mean will be pulled off place if you have one really bad reading. So in practice, your mean could be every bit as bad as our really good data. Whereas if you've got one result that's clearly an outlier, you messed up the pipetting or set the volume wrong or some such, then that will taint the mean, whereas you can kind of ignore it when you're drawing the line of best fit.
And what this means is if you've only got 1 data point at each concentration, you don't know if that's the real value. You don't know if that's the real relationship between X and Y. So you need 3, really, to be sure which one is the real value, if you like.
Okay, we're coming next. Here we're going to start to look at some of the non-scientific thought processes that people demonstrate. Perhaps the most important is illustrated by this. So here we've got triplet measurements. Though, of course, you're even more vulnerable to this if you've got a single measurement. And this group has been given 50 seconds as a target, and one of their 3, or their single measurement, if they're just doing 1, is on 50 seconds. Now, what should they do? Sorry? Okay.
Try it again. So what would it be?
Okay, so that's a thought, and so we'll look at what happens if you do some more replicates and we get this. Now, what are you now going to do? Go up on the line. That's what we should do. What we saw a lot of people doing was having hit that value once, they kind of treated that as being the real result. And all of these are anomalous. It hasn't worked there. It worked on that one, so we're going to keep on trying again until we hit it. So if we come to the next slide, of course this is what we are actually seeing. Again from Andy Dalby's results. What you're looking at is a dispersion of data within which your actual values fall. It could be here, but it could be out here. So now we look at it.
Oh, well, I see that my cat has wandered into the room again. So Schrödinger wants you to know that the definition of insanity is doing the same thing over and over again and expecting different results. We saw a lot of insane behaviour in that.
This is most often attributed to Einstein, but it seems to be one of these sort of delocalized sayings that attaches itself to anyone who's perceived to be wise or intelligent. So, if we come to the next slide, so this is in practice the equivalent to this fallacy we talked about that Popper identified earlier, of looking for positive results instead of looking for negative results. They've seen this one result that supports their conception, and so they're trying again and again and again to replicate that, rather than seeing what is actually going on. And the right answer is still coming from the line of best fit. So as you said, what we should have done is treated this as a dispersion of the data with the line of best fit still giving us the right answer. Not 15 microliters of 15 millimolar ascorbic acid, 16.5 millimolar. Well done.
But some people, as Stuart says, having hit the right concentration once, essentially by accident, believed that that was the only point that mattered, and they ignored all the other points. So, the beginning of critical thinking is distrusting your own data. Instead of saying, phew, what a relief, I've hit the right time by accident. In a sense, you want to be attacking your own data. You want to be disbelieving what you've seen.
What else is the slide telling us? We've already had this. Because although this data is not actually taking us any closer to the time, it is still telling us something quite important. What is it? We've already touched upon this idea when we talked about what the extra data on the graph is telling us. What was that? What does the 3 points on the graph tell us as opposed to the single mean? The spread of the data. So here we've actually got a very nice set of information about the spread of the data. Okay? It's not what they were intending to collect, but it's what they've got. So if we come to the next slide, what does this tell us about their likelihood of hitting the time, even if they use the right concentration, of a single measurement?
How many measurements did they take, and how often did they hit the right time?
Now, we did mention the lectures, and we talked with some groups about the possibility of doing up to 3 replicate runs for your time. How many of you chose to do that?
Do you mean repeating the whole experiment?
No, replicates of their timed run, where one of us was observing. Certainly some groups talked about it and then said, now we'll go for one shot. Okay. Something to think about in writing up why you didn't hit your time. And if you did replicates, you will have information that tells you how likely, broadly speaking, it was that you would hit it on that one run. Okay, come to the next slide. Here's another scenario that we saw happening. I could see some of the people who did this one there. In this case, we're imagining that we hit this time. Our time is, our target is 47 seconds, We don't have the 47 seconds, but we've got this 50 seconds that's quite close. Okay? And certainly one of the things we saw some people, they're sort of nicely collecting their data for their standard curve, and they fall within a couple of seconds, and suddenly it's like a frenzy comes upon them. Instead of carrying on collecting their data nicely, what they do is start trying little changes or tweaks to the reaction condition, sometimes several things at once, to try and move the measurement onto the time. You'll recognise their own behaviour here? Still, and certainly it would probably work for some of you, but still the best and most reliable method to get into the right answer is to finish the standard curve and then make your prediction based upon the whole of the data that you had. Okay. Coming into the territory of filling the data, again, something we don't quite understand. Sometimes people did get a sort of blink of an eye appearance of colour, to make it kind of easy. But in some, you'd get a sort of wisp of colour appear and then fall, and some it would sort of start from the bottom and work up. And one of the things that some groups were quite clearly doing was they were watching the clock and deciding as they watched what point of colour they were going to choose. So effectively they were trying to, consciously or unconsciously, probably unconsciously, they were pushing themselves towards getting the right time. It's a very hard thing to resist. This is why Geoffrey in the earlier lectures was talking about doing blind experiments if you possibly can. So you could have done this quite nicely by agreeing a set time at which a fixed point which was going to be. Say, okay, sometimes it's here at this top when we see the first wisp of colour, or when the colour reaches this point, and keeping the clock hidden from the person who is making the judgment. So instead of the person looking at the clock and doing it, then someone else says, okay, stop it. So there you're blinding yourself, trying to make sure you get an impartial measure.
The point about blinding is not that by observing the experiment you can change the outcome. You can't, by looking at it, make it go any faster or slower. But if you are not blind to the conditions, you can pick arbitrarily the time when you think the experiment has worked. So the importance of blinding is that you remove this arbitrary judgment about when the experiment has worked.
I say it may not be conscious. It may just be sort of, come on, yes, that's it.
And so you decide that the end point of your reaction is when a faint band of colour had appeared. Whereas if you decided that the end point of your reaction is when it had all changed colour, you would have actually had a different time.
So both consistency and rigour are important. And coming into the last points here, so consistency is desirable in that and in other things. This one is a very hard one to criticise for, because we do want all of you to get experience of the lab skills. But certainly some groups were seeing variation in their results because different people were doing the pipetting in different runs. Now, I would say that a better strategy would probably have been to have the same person pipette each reagent each time. But as I say, we didn't really want to tell you to do that because we do want all of you to get experience in pipetting. It's no good if you get to your final year project and you've never done any pipetting because, in the interest of consistency, your friend has done it throughout. But this one's a bit of a different one. A very strange one we saw one group manage is they did all of their standard curve using distilled water, and for reasons I don't think they or we know, switched to tap water for their final run when they were timed. And it put them something like 15 seconds off. They did actually do a very nice supplementary experiment, which would probably make up almost all of the marks, actually, because they then did a new standard curve with the tap water, so they were able to clearly demonstrate why they hit the wrong time.
What's going to be the main difference between the tap water and the distilled water that might affect this reaction? pH. I think it's probably pH. It might be ions.
It could be.
I mean, I don't really know, but my suspicion is that the pH of tap water, which is going to be alkaline, distilled water often falls quite quickly to pH 5 because it's not buffered in any way with heavy ions.
And I suppose the other message from this is that lab skills are important. You aren't just here to learn scientific knowledge. We want you to be scientific practitioners who are able to do things in the lab as well. And you are at a substantial advantage at Westminster because many places, even many better universities than us, have cut down their lab training program because of cost. One reason and another, we haven't done that, so you will get a lot of chance to develop things like the pipetting skill. And I don't know whether we're going to manage this, but Caroline was thinking about turning over one of the last ATS sessions into a lab session to give you pipetting practice. How many of you would be in favour of that? Okay, so we'll pass that on to Caroline and she can organise it.
Incentive mattered in this experiment because if you suck up the solution too rapidly, you will make a difference of perhaps even 20 microliters. And if you're trying to pipette 20 microliters, you've actually put 40 microliters in, then you can't really rely on any of the results. So pipetting seems like something very elementary. It's quite hard to do it well and consistently. And I used to get my PhD students weighing water just so that they could see how variable their technique was. It was quite a surprise to me.
And the other thing we saw quite often is people not being sufficiently careful about keeping making sure their solutions weren't contaminated. It turns out that with this experiment, contamination of the potassium iodide by the hydrogen peroxide seems to set up a chain reaction which had quite substantial effect on subsequent results. I was surprised at how much it did. And usually experiments won't be quite that sensitive. But, for example, if you get your primers mixed up by doing PCR cross-contaminated, then you will have a terrible mess. And it will be an expensive mess too. I think Geoffrey does more PCR in the life than I do, so if you want to add to that.
I am PCR. One problem with mixing the two tubes up inadvertently is that the primers can hybridize to each other and they can form spurious products in the PCR reaction. So it's often important to keep the two primers apart until they're both at the very high temperature that the PCR reaction gives.
And that leads into the last point, which is to encourage you to be thoughtful and reflective as you go along. Some of you are certainly doing this. Some of you are making good observations. You picked up that your results are no longer working properly once you've got this contamination. And you can see quite clearly, because you've got this brown colour in the potassium iodide as the iodine has been formed. Some of you were quite good at picking up on that. And of course, one of the things you could then do is do little tests to check your hypothesis, as this group did with TACMET. So do think about what you're doing, observe what's happening as you go along, and if you think things are going awry, then think of ways that you can check that rather than just sinking into a puddle of despair.
Yeah, one thing that was going wrong was that the potassium iodide was, some of it looked like urine specimens. It was turning yellow. And some people didn't worry about this, and some people did. The people who did worry were the right ones, because the iodine was forming in the Ki solution. And so you were going to get your reaction working whether or not there was any ascorbic present. So you no longer had any control over the system.
Okay, that's the last of my slides. Any questions or comments on that little session?
In our practical, if we had a graph, do we have to scan it in and put it into the report?
That would do no harm.
Or can we do it on Excel?
It's up to you, but I think we might favour a scanned one because that's actual evidence that you did it on the day. Though, do try to make sure it's in a format where it's not 20 megabytes or something.
If you didn't produce a graph to form a hypothesis, what we want to see is your data points. I mean, I know some of you are trying to find by exhaustion where the right point was by collecting 30 data points. If those are your data, report them. That's what you saw. If you didn't make a prediction based on the data, then we don't need to see any made-up graphs.
Okay, I'll hand over to Jeffrey now. And this session, I think, is likely to also feed into finalising your essay as well, in terms of constructing arguments.
And one thing I want to say is that what we've just given you, in a sense, is feed forward. We've given you some criticism about your experiment that you can use. Belt up, please. Boy, you, please be quiet. Feed forward is the idea you can use feedback within the same task. What normally happens is that we give you feedback on an essay, and you can't use that feedback again on that module. You should use the feedback, of course, to influence how you write a subsequent essay in another module, but we know that people are very bad at joining up. So if we give you the opportunity to, if we give you some advice about the way you write up your coursework in advance, that's worth taking. Because advice you get afterwards, you often forget. All you're interested in is your mark. So one thing we talked about in reading and thinking critically was whether we should accept, reject, or suspend judgment. And the example that I showed last week was the mushroom fungus and the claim that it had been used to treat dementia. And you all decided, I think correctly, that what we had to do in that case was suspend judgment. Because until we had gone and read what the Korean scientists had done, unless we knew the details of that experiment, we couldn't really reject it. But you must have a reason for accepting or rejecting. You should not look at the title of a paper which says cancer has been cured, and then just accept that cancer has been cured. Particularly if the claim is very big like that, you must have a look at the quality of the data. That means you have to understand their methods, their procedure, and you have to look at their figures and see whether you believe them or not. And we also mentioned these principles, so we could say that in order to critically think, we need to identify a line of argument, assess it, and then come to a judgment. And then these are the steps beyond. This is what we do now. The outcome of our critical thinking should influence what we do next. What experiment do we set up? What kind of essay do we write? What kind of grant application we're going to make? But the very first step is to identify a line of argument, and that's the thing that students find very difficult. We often say to you, go away and read about this for your literature review, underestimating the difficulty that some of you have, in fact most of you I would say have, actually understanding what even the textbook is trying to tell you. Now you have to get beyond textbooks, you have to get beyond review articles, you have to get into the position where you can quickly scan primary literature and see whether it answers your question. And if you can't do that, you're going to find the literature review next year a struggle. So identifying the arguments the first stage.
And this is one of the reasons why we're starting to get you committed now. And to remind you, you are going to accept this communication test as part of your, at the end of the module, in-class test. So we can sort of set up the game of comparing popular science and real papers as a framework of that, but that's not to say that this is not an important task.
So the first thing to do is find the argument. Now I'm assuming here that you have located a paper that you want to read. We did talk about that in some of the tutorials. Some of you decided not to come, that was your loss, but we did in some tutorials talk about keyword strategies. If you were interested in the relation of drugs and insomnia, what keywords would you put into PubMed to try and retrieve some kind of primary literature? But we're assuming here that we've actually found the paper. We've actually looked at a list of titles, and you remember in one lecture we talked about titles that were either A, relates to B, GM crops and fertiliser, or A does B. So fertiliser poisons GM crops. Quite important to be able to not to be frightened by a title, to understand what the title says, and to decide whether you want to open that paper and look at the abstract. But assuming we've done all that, and we're now at the stage of looking at the abstract's the 200 or 300 words at the beginning of an article that tells you, in a sense, the propaganda, what the scientist writing it wants you to know. You should be very sceptical when you're reading those. You should be sceptical in two senses. You don't necessarily take on trust the punchline at the end of the abstract. If they say, we have conclusively proved that, it might be true, but you don't know until you've looked at the data. The other sense in which you should be sceptical is that you should be looking to see if the abstract answers your question or not. You shouldn't be searching the literature without some idea of what you want to find out. You don't just type cancer into PubMed and retrieve 50,000 hits. You want to know if there's a relationship, for example, between diet and cancer. You might want to know whether papers published in 2012 discuss this. You might want to know whether high-fat diet was related to cancer. You might want to have reduced your searches, the scope of your search with keywords till you've got a manageable number of papers. And so in this abstract, does it deal with the problem that you're trying to answer? Does it tell you anything about high-fat diets and cancer, for example? If it does, then open the paper and look at the introduction. And I recommend that you do no more than skim it. You want to look through the introduction and see whether it seems to be developing an argument, again, that's interesting to you. If suddenly it seems to you that it's only marginally related, for example, to high-fat diets and cancer, it might, for example, be looking at fish oils in feeding farm animals, and you decide that's not really what you want, then I would leave that paper alone. And I often now don't even look at introductions. If you know a field very well, usually the abstract is enough to tell you whether you want to know any more about the paper. And in that position, if you do know the field and you don't want to read through the introduction, you can go straight to the methods. And very often Stuart and I, when we open a paper, will go straight to the methods. First thing we want to know is how they did this experiment and whether we think that's a reasonable approach to answering the question. But never read passively. And do not start at the beginning of a paper and toil all the way through it, waiting for it to tell you something. Unless you're reading actively with your question in mind, you're going to waste an awful lot of time. So close the paper if it doesn't seem to be speaking to your problem, and go to the bits of it that give you the information. And the main bits really are the data and the figures.
Again, coming back to the, if it's not directly relevant, what was this absolutely stupefying number of journals you came up with? The number of scientific journals you came up with?
How many scientific journals there are?
Yes.
I mean, there are at least 10,000.
So there is a stupid amount of information out there. If you try to read every paper that's remotely connected to your subject, you'll be utterly lost. You need to focus. The trendy word a few years ago for it is data mining.
And all of that's on here. So one thing you might look at a figure, if, for example, it was a biochemical graph of the kind we've been showing, is does this actually show, for example, a relationship between X and Y? If they've collected a range of values, have they tried to determine significance? That won't always be appropriate, but sometimes if you want to know that X has made a significant difference to Y, there might be some statistical information. And this is something that I think students could do more of. Very often the authors have not actually understood all of their own data. They've done nice work, well-controlled experiment, but it actually says something else that they're not commenting on. They might be doing more experiments related to these other findings, but you might notice something about their graph that stimulates you to do an experiment, or at least to go and do some more reading. So that's the quick way to finding what's the argument that a scientist is trying to make. And then I would do this, you would do this. We would make a quick précis of what we found. We would write down what the paper is. We might print off the abstract and then make some notes on it. We might say, experiment involved behavioural studies in mice, injected drug, didn't think much about their control, worth looking at again. Something of that sort. You want a, if you like, a record of that paper and how important it is for your research. And then the critique is whether you accept or reject the findings. You can only do that on the basis of their methods and their data. If you understand their methods and you think the methods are good with appropriate controls, and you think those methods led to figure 1 and produced figure 1, then you can accept that claim in that paper. This is the thing where students get distracted, particularly when they're reading through the introduction. They see all kinds of fascinating sidelines. Oh, you know, high fish oil diets. There'll be all kinds of historical information, scientific information, bits and pieces of molecular biology or physiology that they like. Note those down at the side, but don't get bogged down by them. If they're not related to the essay you're writing or the protocol you want to write, leave them alone. And if you are writing this up later, be sparing about quotes. It's not a good idea just to paste chunks of the text, even if you cite it.
And that constitutes plagiarism, even if you cite it.
Yes.
It's making up substantial portions of your right.
You should be able to paraphrase what you read. Again, in this, we keep talking about clear scientific English. You should be able to interpret what you've written. So you can write just a summary of this, one line in your report.
And since plagiarism has come up, the advice that Jane Lewis, now Dean of School, used to give on this is read the text, close it, and then write down your interpretation of it. If you are at any point adapting the text as you go along, then you are in danger of being picked up for plagiarism.
So those are the steps. And the key to it all is actually knowing what your problem is. Unless you've got a question, there's no point embarking on this. Critical thinking means that you are receptive to what people are writing, but it doesn't mean you're passive. Unless you do your literature search with a question in mind, then you won't know how to sift all the information that's available out there. Now, a word on sources. There's textbooks, and the good textbook is a very rare thing, in my opinion. Textbooks have now become part of a cynical publishing industry aimed at students. They want you to hand over £50 for the latest glossy book with lots of photos and wide margins. Some of them are well organised, some of them discuss evidence, but really you want to get quickly beyond the textbook stage. And now if I want to find out something about an emerging field in science, I don't even think of going to a textbook. I think, can I find a recent review on the subject? Will that lead me to the primary literature that I can read? And we're still seeing too much of this at level 5. I've just failed someone on their literature review because, in spite of all my warnings, their only sources were journalism, NHS web pages, lifestyle pages, YouTube, and what I call coffee table science. Magazines about science, like New Scientist. Those are not good sources for scientific writing. You can use them and they might stimulate your interest in a topic, but they're not the sources you should be relying on if you're trying to construct your own line of argument. Wikipedia Is Wikipedia good or bad? Okay, I'm not using bad because I think you think that's the answer I want you to give. If someone, I mean, think critically. If you're asked if something good or bad, you have to say good or bad for what? You know, it's bad if you, it's good if you want someone else to decide the parameters of the problem. So if I want to look up something about DNA methylation, and I'm happy for someone else to decide what is important in the field of DNA methylation, the Wikipedia page might be very good. But if I want to construct my own sources, if I want to decide for myself what the important things are, then Wikipedia might be steering me in a particular way.
I mean, I don't think Geoffrey and I are quite as anti-Wikipedia as many who teach you are. Often pages are clearly written by people who know their stuff, but we're patchy in places because sometimes the people who know their stuff haven't bothered to write a Wikipedia page. For example, some proteins there's lots of, and some that I'm interested in, there's very little. I suppose I could do it myself. And of course it's not peer reviewed. But the other thing that are often very useful for Wikipedia are some of the links. In preparing the lectures for this module, I've found links going directly from Wikipedia to primary sources, sort of research papers from the 18th and 19th century, which I would have a devil of a job finding otherwise.
But be aware, they're the sources that Wikipedia wants you to read. So you will find some of those useful, but you may find, in fact I usually find better information somewhere else. Partly because the page can't be constantly updated. You know, more information comes out all the time in science. There may be later and better sources. So this is why I say textbooks are unlikely to answer your question. At level 5, students say to me, you've asked me to write about the biochemistry of Alzheimer's disease. There's nothing in the library on the biochemistry of Alzheimer's disease. Well, there are actually textbooks written about that, but we don't have any. That's why you have to go to PubMed to find these things. And the best place to start would be a PubMed review on the topic. Journalism, etc., usually cite no sources. And journalists and the kind of health mongers that write NHS and lifestyle pages often have their own agenda. But nonetheless, they might alert you to a question. You know, you might realise that there's some new development in organ transplants, for example, that you're interested in. I've said that Wikipedia pre-selects sources. So you are at their mercy. They've told you what is interesting about this field. So it's better if you're writing an essay, for example, to construct your own source list. And I know students who spend days and days and days doing it because they don't have a good search strategy. I think if you are collecting sources for an essay or a project, take no more than 2 hours over it. That's as much time as it should take for you to collect a sensible number of things that you can read and interpret. It's 2 hours, including the decision whether this is important for you. So 2 hours to select sources that you really do want to use.
Well, you can then bounce on to other sources that you find from your first set, so things that become apparent from your reading are going to be important papers. But you want to be getting on with getting into the subject rather than dithering about what you're going to read in advance.
And often you only know when you begin to write it what these other things are that you want to talk about. I personally find writing is stimulus to thought. In the middle of writing, I think, actually, this is not the topic I want to address at all, or there is some aspect of it here I've neglected. At that point, you look for more sources.
So my logic isn't sound. I need to support that point.
Yes. Yes, indeed. You want to find a source that will, if you like, back up a suspicion that you have, or even a weak hypothesis that you've formed. Do cross-check big claims. Students do love to write in their papers that the example I like to give, you might have heard me give before, is that Alzheimer's is a sexually transmitted disease. So a student who read this and was dead impressed by it wanted to base her whole project on it. I knew the work she was referring to, I didn't say that's rubbish. I said I don't think you've looked at figure 1. When she went and looked at figure 1, she could see the problem. But here's another big claim that I had to, I saw this in something I was reviewing. It was claimed in this review by quite a well-known professor that suicide victims have higher levels of methylated protein in the brain. And this relied on a very weak study of a very small number of suicidal teenagers whose whole life history was quite unknown. The fact that 2 out of 3 of them had higher levels of methylated protein in the brain could have been for any reason at all. So do check the source that they have used to make this claim. Now, I'm conscious of the time. Is Andrew Dolby here?
He's not in yet. He's starting to worry me a little bit. It's probably not. We could maybe go for a break quite soon.
The next session, I don't think I should start, given that we might have the statistics lecture coming on. But the next session, I actually wanted to show you an abstract and what we would do with the introduction and the methods. But I don't think I should embark on that now because we're likely to get interrupted. But instead of talking at a kind of abstract theoretical level about what you should do, I was going to show you what I did do in this case when I saw this article. But I think we better leave that until next week.
Shall we say a 5-minute break while we rustle up